Okay, so welcome to this next video in which we are discussing the ionotropic glutamate receptors. Okay, so in this next video what we're going to turn our attention to is the most interesting but also the most difficult to understand of the ionotropic glutamate receptors, which is the NMDA receptor family of ionotropic glutamate receptors. Okay, and as with the AMPA receptors, I'll tell you what NMDA stands for right at the very end, because again they're labelled after a ligand basically that is an agonist for them. Okay, so we'll discuss what NMDA is right at the end and what it stands for. Okay, right, so the NMDA receptors are also often abbreviated to the NMDARs for short. Okay, right, so again, this is a family of ionotropic glutamate receptors. Okay, so all of the NMDA receptors are tetramers of 4 subunits, which again all have this basic membrane spanning topology structure here. Okay, and the subunits of NMDA receptors can combine with other NMDA receptor subunits to make the tetramers, but they do not mix with the receptor subunits of the other 3 families that we have looked at. Okay, so there's no mixing between the 4 different families. Okay, so same protocol, let's discuss all the different types of NMDA receptor subunit. Okay, so firstly, there is the very important GluN1, and we'll see why GluN1 is so important in a moment, but for now, know that it's in every single NMDA receptor. You can't not have GluN1. Okay, then we have 4 GluN2s. Okay, so there is GluN2A, there is GluN2B, okay, there is then GluN2C, and GluN2D. Okay, so those are the 4 GluN2 NMDA receptor subunits. Okay, then let's move on to the GluN3s. Okay, and again, I should have stressed that the reason there's the N here is for NMDA, the GLU is for glutamate, and then we're just labeling up this specific subunit we're talking about. Okay, then we're talking about the GluN3s now, so we've got 2 GluN3s. We've got GluN3A and we've also got GluN3B. Okay, and those 7 subunits are now the subunits of the NMDA receptors. Okay, so same protocol as always. We now want to discuss how these 7 subunits can actually combine to form NMDA receptors. Well, the first thing to say is that there are absolutely no homotetramers for NMDA receptors. Okay, they're always heterotetramers, and they always contain 2 GluN1 subunits. So that's the starting point for discussing how we can actually build tetramers out of these subunits. The fact that we always have 2 GluN1s, and they always sit next to each other. Okay, so if we're looking at the receptor from above, so I'm now drawing as though we're looking from above now, we're going to have 2 GluN1s sitting next to each other. Okay, so here are the 2 GluN1s. So I'll highlight them up in blue. And all that we now have to discuss is what the other 2 subunits that are sitting opposite them are going to be. Okay, right. So firstly, there are the GluN1, GluN2 NMDA receptors, okay, and these are NMDA receptors where those other 2 subunits that sit opposite the N1 NMDA receptor subunits are within the GluN2 type. Okay, so here is the GluN2 little family of NMDA receptor subunits. Okay, so in all of these GluN1, GluN2 receptors, you're going to have 2 GluN2 subunits sitting here. Now, there are 2 ways that you can do this. There are GluN1, GluN2 diheterotetramers, okay, which are basically going to contain only one type of GluN2 NMDA receptor subunit. Okay, and the reason for that is that we are talking about a diheterotetramer here. Remember what that means. The di means that we only have two different subunits within our tetramer. Okay, so if it's a diheterotetramer, we can only have two different subunits. We've already got one, which is the N1, which means that the other two subunits that we're going to stick in here have to be the same, basically. So they could be two gluN2As, for instance. So we could stick a N2A here and an N2A here. Or they could be two gluN2Bs, or two gluN2Cs, or two gluN2Ds. These are what are known as the gluN1, gluN2 diheterotetramers. Okay, so they contain two gluN1 subunits, and then two identical gluN2 subunits. So I might put gluN2, and then I'll put an X there to denote that you pick one of the four, and that's the only one that you then use. So you use that twice, okay, and you make a diheterotetramer. But there are also triheterotetramers. Okay, so let me give you some examples of triheterotetramers. So trihetero means three different. Okay, so we're going to use three different subunits in our heterotetramer this time. Okay, so we're set with the two gluN1s here, so we can't change those, but we can choose which two gluN2 subunits we put in here, and we can put one gluN2 subunit of one type, and then pick another gluN2 subunit to put in the other position, and that will create us a triheterotetramer, because we'll then have three different subunit types within our overall tetramer. Okay, so let me give you some examples of triheterotetramers then. So, for instance, what we can do is we can have the two gluN1 subunits, which we'll always have, and then we can have gluN2A subunits, okay, well, a gluN2A subunit, and then we can also have a gluN2B subunit. Okay, so this would be an example of a triheterotetramer. Okay, so let me just draw this out for you. So here we have it. This is the view from above again. Okay, now two of our NMDA receptor subunits will be the gluN1 subunits, so these two will be gluN1s. And then the other two subunits that we have, one can be an N2A, okay, and the other can be an N2B. Okay, like so, and that would be an example of the gluN1, gluN2A, gluN2B triheterotetramer, because we've got three different subunits making up the whole tetramer. Now, other examples then of triheterotetramers are, you can also have the two gluN1 subunits with an N2A subunit again, but now with an N2C subunit, okay? In addition, you can also have gluN2A with an N2D subunit, and we also know that N2B can partner with N2D. Okay, so we have gluN1, gluN2A, gluN2C triheterotetramers, where you have the two gluN1s, you have your gluN2A again, but this time this is a gluN2C. You can also change it to a gluN2D here, and then you keep the two gluN1s for this final one here, but then you have a gluN2B and then a gluN2D. Okay, so those are the triheterotetramers that you can form for NMDA receptors. Okay, now so far we've only discussed NMDA receptors where we have gluN1, these two gluN1s, and those will always be there, with two gluN2 subunits. Let's now discuss where we have gluN3 subunits within them. Okay, and we then have NMDA receptors which consist of two gluN1 subunits with a gluN2 subunit, and then also a gluN3 subunit. Okay, so these will also be triheterotetramers because they're going to have three different types of NMDA receptor subunits making up the tetramer. Okay, so they will have two gluN1s, and then they'll have a GluN2 subunit, so one of these ones, and then they'll also have a GluN3 subunit, so one of these ones. Okay, so those also form. And then finally, the final type of NMDA receptor is the NMDA receptors where you have two GluN1 subunits, and then you have two GluN3 subunits. Okay, so these will be the GluN1, GluN3 NMDA receptors. Okay, now in this family of GluN1, GluN3 NMDA receptors, what you can then have is diheterotetramers and also a triheterotetramer. So you can have GluN1 with, for instance, GluN3A. Okay, and this will be a diheterotetramer where you'd have two GluN1 subunits. Okay, so 1, 2, and then in the other two positions you'd have GluN3As basically. Okay, you can also then have the same thing but with GluN3B instead of GluN3A. Okay, so you can have GluN1 with GluN3B, which will contain two GluN1 subunits, then with two GluN3B subunits. Okay, and those two are both examples now of diheterotetramers because they have two different types of subunit making up the tetramer. There is then one final example of a triheterotetramer which will contain two GluN1 subunits with a GluN3A subunit, okay, and then a GluN3B subunit. Okay, so it will have two GluN1 subunits. So if I just draw a little picture here. Okay, here is the channel view from above. Okay, so we have our two GluN1 subunits here, N1 here, N1 here, and then we'll have N3A in one of these sockets and then N3B in the other socket, and that will also be a triheterotetramer because we've got three different types of subunit making up our entire NMDA receptor. Okay, right, so those are the different types of NMDA receptors. The important thing to remember is that you always have two GluN1 subunits, and then you can either have two GluN2 subunits, or you can have two GluN3 subunits, or you can have one GluN2 subunit and one GluN3 subunit. Okay, so it works like that. Right, so let's now talk about the opening of the NMDA receptors. Now, the first thing I need to tell you is that not all of the NMDA receptor subunits bind to glutamate, and this is just another little complexity of the NMDA receptors. Okay, so the GluN1 subunits and also the GluN3 subunits, so GluN3A and GluN3B, these do not actually bind to glutamate. It's the GluN2 subunits which bind to glutamate. These three do not bind to glutamate. Instead, the ligands for these three are glycine and D-serine. Okay, so I'll discuss the structure of these two molecules. So we'll start with glycine, which is the easiest because I don't have to explain optical isomerism of amino acids. Okay, so glycine is the simplest of all the proteinaergic amino acids. So we'll just draw the core amino acid structure firstly. Okay, so here is the core amino acid structure. Here's the carboxylic acid group here, the alpha carbon, and then the amino group. And then the R group of glycine is literally just a hydrogen coming off the alpha carbon. Okay, so this is the structure of glycine. Now let's talk about D-serine, which takes a little bit more explaining. So I'm going to remind you of the two optical isomers that usually exist for amino acids. It doesn't exist for glycine because glycine doesn't actually have a chiral center in it. Okay, so let me draw you a generic amino acid, and I'm going to start by discussing dextro versus larvo-rotatory for a general amino acid, and then we'll talk about specifically serine. Okay, so let me draw out the core amino acid structure again, like so, and then the more general amino acid will have an R group here. Now, if this R group is not a hydrogen, as it is in glycine, then this carbon here, that's at the center of the amino acid structure, this will have 4 different groups coming off it, and therefore it will be a chiral center. Okay? And if you want to understand how this gives rise to optical isomers, we need to go from drawing a silly 2-dimensional representation like this to drawing a 3-dimensional picture. Now, of course, this is doomed to fail without a bit of imagination because I can't draw a 3-dimensional picture, but I can do my best to help your imagination work. Okay, so let's discuss the 2 optical isomers that usually exist for amino acids then. Okay, so let's take the alpha carbon and put it in the plane of the piece of paper. So imagine this carbon atom is sitting nicely on my piece of paper here. Okay, now also in the plane of the piece of paper I am going to have the hydrogen that comes off the alpha carbon, so this hydrogen here. So I've just extended this little bond, and now the hydrogen atom is also sitting in my piece of paper here. Now I can also get one more bond to sit in this plane of paper, and I think I'll go for, let's do the amino group. Okay, so here's the amino group here, and I've also got this nitrogen atom to sit nicely in my plane of paper. I can do that. The other 2 groups I cannot possibly get to sit in the piece of paper. One of them is going to come off here and come out towards us at this sort of angle here. Okay, so it's going to come off like this. And one of them is going to go into the page away from us. Okay, so the question is which one comes out of the piece of paper and which one goes into the piece of paper, and that's the question of optical isomerism. You can have 2 different ways of doing this, and basically you can't interchange between the 2 without performing a chemical reaction. So let's, for now, say that the R group can come out of the page towards us, whilst the carboxylic acid group can go into the page away from us. Okay, so here's my bond coming out of the page, here's the R group, and then going into the page away from us, here is the carboxylic acid group. Okay, now the other one then, the other optical isomer, okay, would have, let's try and draw it exactly the same. So here is the alpha carbon with the hydrogen coming off it and the amino group, and they're all in the plane of the piece of paper. And now this time I'm going to let the carboxylic acid group come out of the piece of paper at us. Okay? And then I'm going to let the R group go into the piece of paper away from us. Now, no way that you can just rotate this molecule can you ever turn it into this. Okay, so you can't just merely rotate this molecule around, or better yet, you can't rotate yourself and just change the way you look at this and make it look like that. Because to make this look like this, you have to leave the hydrogen, the carbon, and the amino group exactly where they are, and then you can't move these 2. Okay, so to swap these 2 round, what you'd have to do is break this bond here, break this bond here, then swap them around, i.e. you'd have to perform a chemical reaction. So you cannot turn this one into this one without performing a chemical reaction. Okay, so they are different molecules, and they are known as optical isomers of one another. Okay, right, so there are 2 optical isomers of amino acids. Now there is another term that people often use with regards to this, and they use the term enantiomers. Now the term enantiomer is much more specialized than optical isomer. Enantiomer literally means, well, it means that they are very special optical isomers of one another. It means that this one is actually the mirror image of this one. Okay, and how you can see that is that if this one was to look into a mirror, okay, and this takes a little bit of 3-dimensional visualization. Okay, if this one was to look into a mirror, what would it see? Well, it would actually see a molecule like this. Let me draw its reflection for you. Okay, so here's the alpha carbon with the hydrogen coming off. Here's the amino group going backwards. And now coming out of the page towards us, we've got the R group. Okay, and then going into the page away from us, we've then got the carboxylic acid group, which you have to excuse me, I'm drawing across the mirror, but you get the point. Okay, now, my claim is that if I just rotate this round 180 degrees, it's exactly what I've got here. So imagine just rotating that around so that the amino group lies on top of this amino group, and the alpha carbon lies on top of this alpha carbon, and the hydrogen lies on top of this hydrogen. Okay, the R group will then now go into the page away from us just like this, because I've rotated it around 180 degrees, and the carboxylic acid group will now come out of the page just like this. Okay, so that's why people talk about enantiomers when they're talking about the optical isomerism of amino acids. Enantiomers is much rarer term in general optical isomerism. So you have loads of molecules that are optical isomers of each other. It's rare that they are actually enantiomers when they're actually mirror images of one another. When you have a molecule which only has one chiral center like this, then yes, the two optical isomers will be enantiomers. Okay, there's only two optical isomers and they will be enantiomers. But when you have more chiral centers, then it becomes much more difficult to say that two optical isomers are enantiomers. Okay, it's much less likely that they will be enantiomers then. Okay, right. So there are ways of naming the two enantiomers of amino acids. Okay, one of them is known as the lavorotatory enantiomer, and one is known as the dextrorotatory enantiomer. Now, how do you remember which is which? Well, basically, what you have to do is imagine that you are sitting up here with the hydrogen atom. So imagine you're sitting perched on top of the hydrogen atom and you're looking down at what you see from above. Okay, and you are going to try and read a word. You are going to try and read the word corn. Okay, and the way you spell this is you get the CO from the carboxylic acid group, you get the R from the R group, and you get the N from the amino group. Now, in the case of this one here, which way are you going to have to turn your head? Well, your head's going to start off looking at the CO here. Okay, it's then going to go to the R, so it's going to turn this way, and then it's going to go to the amino group here. So you're going to turn your head in the clockwise direction. Okay, now if you turn your head in the clockwise direction to read corn, then you are sitting on top of the lavorotatory, okay, and this is a big word, so I hope it's going to fit in here, good, lavorotatory isomer, or the lavorotatory enantiomer, if you're being posh. Okay, or merely the L isomer. So when people talk about the L amino acids, this is what they mean. They mean that if they sat on top of the hydrogen coming off the alpha carbon and read the word corn, their head would go round in the clockwise direction. Meanwhile, if we look at this other optical isomer, if we now want to sit on top of that alpha carbon, or let's do it on this picture because this one's better than this one. If we sat on top of this hydrogen here and wanted to read the word corn, what would we have to do this time? Well, we'd start here with CO, then we go here to R, and then we go here to N. So our head this time would go round in the anti-clockwise direction. And if you are sitting on top of the alpha carbon and your head has to go round in the anti-clockwise direction to read corn, then you are sitting on a dextrorotatory enantiomer of that amino acid. Okay, or the D enantiomer. So that is what is meant by the L enantiomer and the D enantiomers of amino acids. Now, most of the amino acids that we have in cells are the L enantiomers, not the D enantiomers. Okay, so D-serine is a weird one, basically, which is why people have stressed the optical isomerism. If people tell you about an amino acid and they don't tell you what the optical isomerism is, you can assume they mean the L enantiomer. If someone wants to tell you about the D enantiomer, they will stress it like so. They will call it D-serine. Okay, so if someone just says serine, you assume they're talking about L-serine. If someone says D-serine, then you know they're talking about the D enantiomer. Okay, right. So if we now draw a picture of D-serine then, so we know that it's got to be of this form here. Okay, so all we now need to substitute in is what the R group of serine actually is. Okay, so let's draw this picture again. Here's the alpha carbon with the amino group and the hydrogen coming off it. The carboxylic acid group is going to come out of the page towards us. okay, like so. And then the R group is going to go into the page away from us, and in this case the R group is going to be a methylene group, CH2, and then it's going to have an alcohol group coming off. Okay, so that's the structure then of D-serine. So both glycine and D-serine are agonists for the gluN1 subunit, the gluN3 subunit, and also the gluN3B subunit. So these subunits bind to glycine and D-serine, but not glutamate. Okay, now what does this mean? Well, it means, it is significant because it means now that to open, our NMDA receptors are always going to require either glycine or D-serine, and they're far more likely to get glycine than D-serine, so it's usually glycine. Okay, so they're going to always require glycine because we always have two gluN1 subunits within our NMDA receptor. Now, if you've then got a gluN1, gluN2 NMDA receptor, then you will then have two gluN2 subunits sitting alongside the two gluN1 subunits, and you'll therefore also require 2 molecules of glutamate to activate the gluN2 subunits. But if you've got more gluN3 subunits, okay, so if you haven't got any gluN2 subunits, then you're not going to require glutamate. So we'll turn our attention next to these ones. gluN1, gluN2, gluN3 triheterotetramers. Okay, remember these consisted, did I ever draw a picture of this? I don't think I did. Okay, so these consisted of 2 gluN1 subunits as always. Okay, and those both want glycine, not glutamate. Then we had a gluN2 subunit, and then a gluN3 subunit. Okay, so now we're going to have 3 subunits that want glycine and only 1 that wants glutamate. Okay, but finally, look at these ones, the gluN1, gluN3 ones. Those consist of 2 gluN1s and 2 gluN3s. So this isn't actually a glutamate receptor at all. They all want glycine. Okay, so this was a bit of a novelty when people first realized this, because glycine was always thought to be a purely inhibitory neurotransmitter. Remember, I told you when we were discussing the cis-loop ligand-gated ion channels, or the nicotine-like receptors, that you have glycine receptors in your spinal cord, which are cis-loop ligand-gated ion channels. They're these pentameric receptors with totally different membrane-spanning topologies. Okay, and those receptors inhibit neurons. They open and allow chloride ions to come into the cell, inhibiting neurons just like GABA A receptors. Those were the archetypal glycine receptors. They were inhibitory. But now we found these NMDA glutamate receptors, which are completely gated by glycine and are excitatory receptors, basically. These are going to excite cells. They're going to depolarize the electrical potential difference across the cell membrane. So this was a bit of a shock when people first realized that there were excitatory glycine receptors, and they were in the form of some of these NMDA receptors that weren't actually sensitive at all to glutamate. Okay, now, these are not awfully common. Okay, most of the NMDA receptors at least have 1 N2 subunit in, if not 2 N2 subunits in. So we're going to now focus on the ones which do have at least 1 N2 subunit in, if not 2. Most of them will have 2 N2 subunits in. Okay, because those are the ones that are going to be gated by glutamate. Right, okay, so, turning back over here then. So, these gluN1 subunits then, and if you have one, a gluN3 subunit. So we are paying attention now to the NMDA receptors which have at least 1 gluN2 subunit in, so maximum they have 1 gluN3 subunit in, if not 2 gluN2 subunits. But no matter what, they will always have 2 gluN1 subunits within, and these 2 gluN1 subunits will want glycine basically to open. So NMDA receptors always need some glycine to open. They need both glycine and glutamate. Okay? So if you have 2 gluN2 subunits, you're going to need 2 glutamates, okay, and then 2 glycines to open you. Okay, so these are the gluN1, gluN2 receptors. On the other hand, if you have if you have two gluN1 subunits, then you have one gluN2 subunit, and then finally also one gluN3 subunit. Okay, so if you're one of those tri-heterotetramers, which remember we discussed here, okay, you're going to require 3 glycines to open you and only 1 glutamate. Okay, right, so let's now discuss how we actually open an NMDA receptor and what happens when they do open. Okay, so let's get a new piece of paper for this. So, the first thing to say is that usually the problem of whether you have glycine or not is not a problem. Okay, usually the amount of extracellular glycine is enough that you do not need to worry about those 2 gluN1 subunits having their glycine, or if you have it, the gluN3 subunit as well having its glycine, which means that those ligand binding domains always have their glycine bound to them, and therefore to open the receptor all you now need is the glutamate, either 1 glutamate if you've only got 1 gluN2 subunit, or 2 glutamates if you've got 2 gluN2 subunits. Okay, so let's now discuss what glutamate is going to do to the NMDA receptors. We're not going to mention the glycine again, okay? We're just assuming now that that is there, bound, and we don't need to worry about it. Okay, so opening the NMDA receptors then. It's more complicated than it seems, okay? It's more complicated than for AMPA and kainate receptors, and the complexity here is what gives rise to how powerful and interesting NMDA receptors are. Okay, so let's draw our NMDA receptor here, like so, and it will be this tetramer, remember, and it will contain 2 N1 subunits, okay, here and here, and then we've got our other 2 subunits, which are either both gluN2s, most likely, or maybe 1 gluN2 and 1 gluN3. Okay, right, so what's then going to happen is the glutamate is going to come and bind, and that will open the channel. Now the question is, does any current move through? And the answer is no. Not if the electrical potential difference across the cell membrane is at the resting level. Okay, so let's discuss why. So basically, at the resting electrical potential difference across the cell membrane, which is negative 65 millivolts, the NMDA receptor is going to have a magnesium ion sitting in it, and this magnesium ion will be sitting in it even before the glutamate has bound. So basically, blocking the pore of the NMDA receptor is this magnesium ion, okay, shown here in blue. Okay, now it will be more inside the receptor than this, but to get the point across, here it is, blocking that pore there. Okay, so this is a magnesium ion, and it's on the extracellular side of the NMDA receptor. So, why is the magnesium ion doing this? Well, basically, the magnesium ion wants to get to the place where the electrical potential is lower, which, remember, is the intracellular compartment. The intracellular compartment has a lower electrical potential, which is lower than the extracellular compartment's electrical potential by 65 millivolts. Okay, magnesium is a divalent cation. It has a double positive charge. It wants to be in the intracellular compartment. So it tries to get through and then gets stuck, basically. Okay, and this is even before the glutamate is bound, okay? So no glutamate yet. It doesn't need the glutamate to have bound to try and get through there. It's sitting in there already blocking the pore. Okay, right. Then what's going to happen is glutamate is going to be released onto our NMDA receptor, and I suppose I should tell you where NMDA receptors are generally localized. Okay, so once again, here is our presynaptic neuron, which will be releasing glutamate, and here is our postsynaptic neuron. Now, NMDA receptors are usually found on postsynaptic neurons, where you also have AMPA receptors. Okay, so where you have AMPA receptors, you generally also have NMDA receptors co-localized with them. So here, let's say this is an AMPA receptor. We'll color this in orange here. Okay, and let's say this over here, in turquoise, this is our NMDA receptor. Okay, right. So what will happen now is when the presynaptic neuron releases the glutamate will diffuse across the synaptic cleft, bind to the NMDA receptor, and you'll either need two of them if you've got two GluN2 subunits, or one of them if you've only got one. Okay, and that will cause the NMDA receptor to go into the open conformation, but the magnesium ion is still there and nothing is going to move through. Now, if the magnesium ion was not there, the NMDA receptor would be a fantastic pore for sodium, potassium, and also, and very importantly, calcium ions. NMDA receptors have a fantastic permeability to calcium ions, and this is extraordinarily important for their function. Okay, we will come back to that. Remember, the calcium concentration is around 1.5 millimolar extracellularly and 100 nanomolar intracellularly. So there is this 15,000-fold concentration gradient favouring the movement of calcium into the cell. So whenever you open an NMDA receptor, what's going to happen is you're going to get calcium moving in. You don't even need to ask what's happening to the electrical potential difference across the cell membrane. No physiological electrical potential difference across this cell membrane is going to be able to oppose a 15,000-fold gradient. Okay, so when you open a calcium channel in the cell membrane, you always get calcium moving in. Okay, so what we need to do then is we somehow need to get this magnesium ion out. Okay, so how do you get the magnesium ion out? Well, how did we get it in? What caused it to come in the first place? Well, it was this electrical potential difference across the cell membrane that was driving the magnesium ion in. That was what was giving it the drive to try and get into the cell. So, if we remove this electrical potential difference, would that get the magnesium ion out? Well, it would, basically. If we depolarize the electrical potential difference across the cell membrane, what will happen is that magnesium ion will no longer feel the same sort of drive to get into the cell as it would at negative 65 millivolts, and it will then diffuse off, basically, and unblock our NMDA receptor. If we then stimulate the NMDA receptor with glutamate, what will happen is the NMDA receptor will open in response to the glutamate, and now will allow sodium, potassium, and most importantly, calcium ions to move through it. So you'll get calcium ions coming into the cell. Okay, and we don't really care about what the effect with regards to depolarization is going to be. What's important for these NMDA receptors with regards to their function is that they allow calcium to come in. Okay, and we'll spend more time discussing that in the next video when we discuss long-term potentiation. But the final thing I want to say before we end this video, and then in the next video move on to long-term potentiation, is I want to talk about how much you have to depolarize the electrical potential difference across the cell membrane to get that magnesium ion to shift out of there. Okay, so generally you need to depolarize the cell membrane to something between negative 40 millivolts and negative 20 millivolts. Okay, so somewhere around that level, the magnesium ion will move out. Okay, and it's because the urge for the magnesium ion to get into the intracellular compartment is going to be hugely reduced when you depolarize the electrical potential difference to this sort of level, basically, and that will mean that it doesn't try so hard to get into the intracellular compartment and therefore clears the pore of the NMDA receptor. Okay, but we'll continue this discussion and we'll see how the NMDA receptors are extremely important in a phenomenon known as long-term potentiation, or LTP, in the next video.